my catchphrase has been model everything. You know, whenever people sort of say that they have a specific task and they ask, how could I use neural networks to solve this problem? My answer is always, okay, gather all the data you can get, everything that's sort of related to this problem, and model it all at once. Get it all into one joint model. And then whatever task it was that you were looking at can probably be expressed as a conditional sampling problem.
Welcome to Let's Talk Research, the official InstaDeep podcast, where we dive into innovative AI research and the stories and people behind it. My name is Bora Gilola. I'm a research scientist here at InstaDeep.
And I'm Massimo Bortone. I'm also a research scientist at InstaDeep, and we will be your hosts for this podcast. Today, we're kicking off our first ever episode with someone who has kind of reshaped how we think about generative models. Senior staff research scientist Alex Graves.
Thank you very much. I'm very glad to be here.
It's really nice to have you. So you may already know Alex from some work, foundational work he's done on neural networks and generative modeling, including RNNs, long short-term memory, and neural Turing machines, if I'm correct.
Yes.
But today you're here to speak about something completely different.
Bayesian flow networks, or BFNs as we like to call them, are a new way of generative modeling. It's a novel paradigm. It's a new approach to it. And the idea is really that we use Bayesian updates to update the parameters of a distribution or beliefs about data. And then these get fed into a model. And that essentially allows some very interesting mathematics, but also some very interesting structure to emerge from that. Alex, welcome. I think we can just start right off with the origin story of BFNs. What were the inspirations behind it? How did you come up with the idea? And how did you end up developing it?
Yeah, it's an interesting story and quite a long story. I was working on autoregressive models a lot back in, this is going back to sort of 2010 and even earlier than that. And I started thinking that, a limitation to those types of models are that they're very rigid in the way that they model the data. So, an autoregressive model, like a typical large language model, for example, you break the data down into a series of chunks, like a series of tokens in language, and you predict each token one after another. And you kind of, you condition every prediction on the previous ones. And these models are extremely powerful, but they always felt a little bit rigid and unnatural to me in two different ways. One way is that the order that they predict the data in is fixed and predetermined. And the other one is that for every token, they have to kind of predict it absolutely. So, the prediction is sort of binary. It's either fully predicted a token or it knows nothing about it. And it always seemed to me that it would be nice to relax both of those constraints, to have something that could operate in a more kind of dynamic or kind of model-defined order, but also have something that learned about the data in a more continuous and non-binary way, in the sense of gathering a certain amount of information about a certain region or subset of the data, and then kind of subsequently refining that. And it always struck me as a more human approach to modeling data, in the sense that, people don't, when presented with a new scene, for example, we don't immediately take in all the information at once, nor do we break it down into, a series of discrete pieces and predict one after another. We kind of, our eyes move around in a complex way. We gather a little bit of information about one part of the scene, a little bit about another part of the scene, and we build up this kind of picture in a kind of fuzzy way. And so all of those things were kind of swirling around in my head. And I started thinking about ways to kind of relax this autoregressive system that I was using. And then, up until then, that was, I'd say the majority of my research was based around that. This was in kind of language modeling, speech recognition, things like that. And the first sort of effort I made way back then was a system that kind of learned the order of an autoregressive sequence. And it kind of learned through like a reinforcement learning type procedure. It sort of learned, I always thought of it as like a hangman network or a crossword network. Given a sequence that's all blank, fill in the blanks one at a time in an order decided by the network. And that did some interesting things. Like for when I fed it to natural language, I found that it would predict the second letter of every word first, and then go back and predict the first one. I think because second letters in English tend to have lower entropy than first letters. They're often vowels. Anyway, didn't seem like a particularly fruitful research direction at the time. I never published that work. I just kind of, it got, put on the shelf and left there. And then a few years later, I started thinking about the other side of this story, which is, why can't the network kind of partially learn about each part of the data at every modeling step? And I didn't have a method, I hadn't thought of a way of doing that at the time. I remember having some discussions with people I worked with, and, we agreed that it seemed like a nice thing to do, but couldn't really see a way of doing it. And then much later, and this is probably around 2020, I suddenly thought, oh, maybe there's a really easy way. You just add some noise to the data. And then I realized that if you added noise and then did a Bayesian update, just sort of using Bayes' rule, like sequential Bayesian updates, then you had a system that could kind of continuously go from learning everything about the next piece of data to learning nothing. Like as the amount of noise increases, the amount of information that the system gathers decreases. And that was kind of like the point when BFNs really crystallized. It'd been sort of, it's interesting to think about how long ideas can kind of sit on the shelf or sit in the back of your mind before they come together at some point.
So that's super interesting to hear that you already back then were working on sort of trying to understand the limitations of autoregressive models, because this is something I've done personally in my PhD as well, in a completely different context, more in like quantum physics, but I kind of arrived at similar maybe, or some similar conclusions as in sort of the limitations of this one-dimensional ordering across the data, how it limits in a sense, the expressivity of your model. Would you say this is something that you were focused on as well, or was this the problem that you were trying to tackle initially?
No, definitely the ordering, and I think it's clear, when you look at text, which is the area where autoregressive modeling remains really dominant, it's kind of clear that there is a natural ordering. I mean, we do write, in the case of English, we write left to right, and,
yes.
it's a sequence of tokens that kind of builds on the previous tokens. But then when you start looking at other types of data, so, early on, people, before diffusion models really caught on, people were using autoregressive models for images as well. And there it felt particularly unnatural, because you're taking this two-dimensional grid and kind of turning it into like this one-dimensional raster scan in some arbitrary order through the data.
Yeah.
And I think that was clear to everyone that didn't seem right. Like you're imposing an order that doesn't exist. And I think there's an interesting kind of space there of, like, for example, graph data. You can always serialize a graph and put it in a particular order, but it's sort of arbitrary, or somewhat arbitrary, what order you choose.
Yes, and I think also the order that you choose, or you end up choosing, is then it imposes a certain kind of long-range correlation, right? Because
Yes.
you can always change the order and obtain completely different types of interactions at different distances across your data. So I think then, the choice of ordering really becomes important, or it impacts your the ability of your model to learn quite significantly. And I wonder why in text it doesn't really matter that much. Maybe
it's interesting, but it's actually, it also reflects on the changes in model architecture have influenced this. So, like in the early days when I was working with recurrent neural networks and long short-term memory, I was very kind of, vexed by this notion of, long-range dependencies. The whole idea of long short-term memory was to have a longer memory, to be able to deal with longer dependencies. But it wasn't until attention-based models took over that it really became kind of almost irrelevant how far apart two things were in the input sequence. So, up until that point, it really seemed like a big deal which order you chose to model your autoregressive data in, because that really defines how strongly, basically, the closer any two tokens or elements are in the sequence, the more strongly the model relates them, like the stronger the correlation. So yeah, I think there's an interesting interplay there between, you know, the let's say the modeling system and the architecture used to define it.
Right.
And Alex, in the paper, you kind of conceptualize the idea as this noisy communication protocol, right? Which, coming at it from an ML background, but not having really seen that sort of approach to it, was quite foreign to me to begin with. Do you mind elaborating on that a little bit more and explaining how that ties into everything?
Yeah, I think there's a whole other story there, which sort of goes back to these kind of different schools of thought in machine learning. So I've always kind of belonged to this compression-based way of thinking, which I think I partly owe to my PhD supervisor, Jürgen Schmidhuber, who really thought of, you know, intelligence as a kind of sequential compression, you know, algorithm. And basically, you know, there's one way of thinking about, you know, sort of modeling data in general is to think that you're building a compressor of the data. You know, it just, you know, basically goes back to this, you know, relationship between log probabilities and code lengths, which is, you know, obviously like probably the most fundamental kind of equation in machine learning. But yes, it's for me, you know, a lot of systems that most people think of in terms of kind of, you know, prior probabilities and Bayesian statistics, I tended to think of in terms of communication protocols. So to give an example, variational autoencoders are that type of system. I tend to think of it as a communication system. Like there's a prior that kind of receives a bunch of information about the data. The cost of that information is given by the Kullback-Leibler divergence between the, you know, the prior and the data distribution, and then you have a kind of a reconstruction cost where, you know, given once the prior has received the information, it then attempts to reconstruct the data, and you can conceptualize that as a kind of sender receiver. And that's just how, for me, that's always been a much more natural way of thinking about the problem, rather than thinking about it in terms of, you know, directly in terms of probability distributions. And so, yeah, I think having started from there, it felt very natural to say, okay, there's this sequential process at every stage of, you know, for any generative model. Like in order to build a powerful generative model like the ones we see these days, they have to, you know, the whole point of them is that they operate on this kind of immensely complex high dimensional data, things like images and videos and text, where every, you know, if you think of every, you know, pixel in a video as a separate variable, they all obviously interact with one another in very complex ways. So, you know, if you think about it in terms of sort of old-fashioned statistical modeling, it's this impossibly complex high dimensional space. And the way all of these models work is basically they divide and conquer, right? They break this huge high dimensional space down into a series of many iterative steps. For autoregressive models, it's really straightforward. It's always, you know, predict one more pixel given the previous ones, one more token given the previous ones. For models like diffusion and also like Bayesian flow networks, it's kind of more complex. You're gathering kind of varying amounts of information about all of the variables at every step. But it's still, I think, a kind of a dialogue or a series of messages. You know, at every point there's an update where the network receives some more information about the data, and that update has a cost, and that's basically always can be thought of as a communication cost, a coding cost, where, you know, it's as if a sender who knows the data is selectively sending the information, a little package of information at a time. And once the receiver has that information, they can then improve their predictions. And the point is that by improving their predictions, they reduce the cost of the next piece of information coming their way, because they already have a sense of what it's going to be. And so it's a thought experiment in some sense. It's a concept. It isn't necessary, right? You know, for most people, I think most people who are kind of, you know, familiar with the machine learning generative AI field, it's easier to think of BFNs as something akin to diffusion or something even akin to a variational autoencoder. You can think of it as a very deep autoencoder loss where there's a kind of an elbow loss with a reconstruction term. But conceptually, I prefer to think in terms of messages, and I think it's an important difference to distinction to make, where you can end up with exactly the same mathematics, you can end up with the same code, you're going to implement the same thing, but you've come at it from a different angle. And I think some people would say, well, then what's the point? If you end up in the same place, then who cares what the different angle is? But the point is that the angle you come from is the generator of new ideas. That's the thing that gives you a sense of new directions you could take. And so my feeling and my instinct is that with Bayesian flow networks, kind of deriving it from this principle of a communication channel, a communication protocol, will open the door to kind of new variants, new ways of kind of transmitting information between these kind of fictional Alice and Bob characters.
Alex, you mentioned Alice and Bob here. For the uninitiated, who are these two characters?
So Alice and Bob are fictional characters engaged in a dialogue that were first introduced in the cryptography literature. Essentially, I think they were a less dry way of talking about A and B. And they give a nice kind of anthropomorphic angle to this notion of packets of information being sent and received. That is how I kind of conceptualize Bayesian flow networks and how I like to think about Bayesian updates in general.
Oh, that's very cool. And so, just to kind of think about this a little bit more, you mentioned that BFNs are actually mathematically ended up being relatively close to diffusion models.
Yes.
But you came at it from a completely different angle, right?
Yeah.
So how was that? Can you talk a little bit more about that story of how these two things emerged and then how they met? And
yeah, I mean, it was kind of interesting. As I said, I'd been thinking about this idea of kind of noisy predictions for a long time. And then, in around about 2020, I started thinking, you could just add noise to the data and then do a Bayesian update. And then shortly after that, I read about diffusion models, which were really taking off at that point. So they, originally introduced back in 2015, but they kind of lay dormant until 2019 when there were some breakthrough results and people showed that you could really get, very strong image models out of diffusion networks with a few modifications. I mean, as always, the devil is in the details. And then when I first saw that, I kind of thought, okay, forget it. This has already been done, right? This is a dead end. But then as I looked further, I saw, okay, it's very similar, and in some cases it's going to end up being mathematically identical, but it is different, and it's coming from a different perspective. And I think it has, it has given me scope to kind of go off in different directions from the way that the majority of the diffusion field is going. I think one place where the differences become quite is maybe more apparent is when looking at categorical data, because the Bayesian update process kind of naturally ends up being continuous because it operates, rather than operating directly on the data like sort of standard discrete diffusion does, it operates on the statistics of a distribution over the data. So I mean, maybe in some ways a sort of elevator pitch for Bayesian flow networks is diffusion on distributions. So
I think I when I read the paper the first time, that's really the line that clicked for me. Like, you're modeling not data directly, but you're modeling the distribution that models the data.
Exactly.
And I think that's it's a nice way, I think, of having sort of the same framework be sort of detached from the type of data that you're trying to model. Because if you're modeling the distribution that models the data rather than the data itself, it doesn't matter whether it's discrete or continuous, you can apply the same framework to whatever kind of data. And I think that's probably the leverage that you can have with BFNs compared to diffusion.
Yeah, so it's sort of like one step of what's the word I'm looking at? It's one step more abstract. It's sort of like a meta diffusion process that operates on the distribution. But I mean, at the same time, I should say that, you know, people have looked at diffusion on the probability simplex, which does end up being quite similar, not identical, but similar to discrete Bayesian flow networks. But I think my feeling is that the difference there is that it's sort of somewhat more arbitrary. You know, I think people looked at discrete diffusion and found that it wasn't working so well. And they thought, okay, it would be nicer to make this continuous. How do we get this in a continuous space? Well, the natural thing is to say, well, let's just do diffusion like we're doing it now, only drop it into the space of that we know that, you know, probabilities exist on. But I felt that it was nice that in the case of Bayesian flow networks, that emerges directly from the kind of the mathematical principles. It's not, it wasn't like an arbitrary choice in the way that it is with diffusion.
Would you be able to say what kind of problems do you circumvent by going into this more abstract level that, for example, discrete diffusion struggles with?
Yeah, so I think in general, well, specifically one thing that's lacking from discrete diffusion, as in diffusion directly on discrete data, is, you know, just that it is discrete, and that means that the generative process is no longer continuous. Because it's not continuous, you can't pass a gradient through it. You can't backprop through it in simple terms. And that means that you don't have access to these kind of gradient-based guidance methods, which, you know, we've been using to great effect with biological data. So I think you just get, keeping everything in a continuous space gives you more control over the generative process, I think is the real sort of practical advantage there.
Yeah, and I think from an application point of view, that's really interesting, because that's really where the generative part of the generative model becomes interesting, when you can actually guide it, or like partially inform it, and then ask the model, can you fill this in? Yeah, and I think we'll see more in the second episode.
Yeah, I think we'll come back to that, and that's definitely what we found in practice is, in some sense, what the model provides is a joint distribution over all the data and over many different types of data. But in practice, it's never really the joint distribution you want. It's always a conditional distribution that allows you to guide and to constrain what it is that the model's doing.
Yeah, and in terms of kind of a common task of that sort, so sequence inpainting, let's say, right, the advantage of these sorts of models is that you don't have to train them with the specific inpainting task in mind, right? You don't have to predefine what bits of the sequence you're going to mask away, as you would do with, say, a bird-style transformer, right?
Yes, and I think that's been, just as a sort of general guiding principle, I'd say over the last few years, like my catchphrase has been model everything. You know, whenever people sort of say that they have a specific task and they ask, you know, how could I use neural networks to solve this problem? My answer is always, okay, gather all the data you can get, everything that's sort of related to this problem, and model it all at once. Get it all into one joint model. And then whatever task it was that you were looking at can probably be expressed as a conditional sampling problem. So even something like image classification, rather than just training a model to classify images, you can train a joint model over images and classes, and maybe over captions and over other associated metadata you might have about the images too. And then classification just becomes a specific example of a conditional sampling problem. You're saying, okay, given the pixels in the image, tell me the class, or tell me the caption. And doing that, really, the big advantage of that kind of approach is that you get a lot more, you kind of squeeze more juice out of your data, you know, because you're really training the model to learn everything it can about the data. And that means, you know, it overfits less and it generalizes best. This is especially important in areas where data is more restricted. You know, I think over the last few years in generative AI, we've seen these huge leaps in areas like text modeling and image modeling, where there's just massive amounts of data, and, you know, being efficient with data has been less on the agenda than it used to be. Yeah. But this isn't the case with scientific data, where you're often quite restricted. And I think there it's really important to get all of the kind of signal you can out of the data. And so I think I've lost the thread of the question.
No. I mean, it's there's also a certain beauty to this idea of, I can just train one model on all of my data, and then the task is completely up to me after that, right? It may change down the line. I can have task 1, task 2, but I can always just use the same model. And it's just about how I end up prompting the model, right? How I end up interacting with it.
And it's good that you use the word prompt, because actually, of course, these large language models and chatbots they're doing the same thing, right? They're learning a joint distribution over huge blocks of text, an unconditional joint distribution. And then you use it by steering the model, and steering it means providing a prompt, which is just a conditional sample. And of course, it's a form of conditional sampling that plays really nicely with autoregressive models in particular. So I think that's another reason that autoregressive models are so preeminent in text, is that that is actually a very natural way to interact with text. Set a prompt, and then actually I have an interesting story there. I actually had an early form of prompt engineering in a paper I wrote on handwriting generation back in 2013, generating sequences with recurrent neural networks. And in that system, I had a model trained to do handwriting synthesis, as it was called. So basically take some text, feed it into the network, and generate the handwriting. So already you have a conditional distribution here where you're prompting with the text, but okay, that in some sense wasn't prompt engineered. That was just fed, it was trained as a conditional model to start with. The prompt engineering came when I wanted to generate handwriting with a particular style. And I found that if I basically fed the network some existing handwriting, by a real writer, along with the text that they'd written, and then just appended to that the text that I wanted it to write afterwards, and then ran it forwards, it basically just naturally continued with the style that it had already had. So you sort of, it was prompted with a particular style, and then it just carried on. And it was very exciting and surprising at the time to see how well that worked. And I think it's really that's been a big part of the of the story of what's made large language models so exciting, is that the prompt information really carries through. That really completely sort of shapes what it is, the way that the model responds.
I'd like to maybe go back to your what you just said recently, is about being efficient with your data. So similarly, during my PhD, there's one limitation in quantum physics, is that the problem is exponential. So you have to be efficient with your data, because you can't go through these high dimensional spaces efficiently otherwise. What would you say has sort of shaped this view of doing machine learning to be sort of efficient with your data rather than just scaling everywhere?
I think, to be honest, the scaling approach is more recent. If I think back to 10 years ago, even further, we were always working with small data sets, and everything was always about data efficiency.
Yeah.
And back then, regularization methods like dropout, I worked on methods with adaptive weight noise and things like those seemed much more important back then, because you couldn't just get more data. If in some sense that the best cure for overfitting is always more data.
Yeah.
But I would say it's sort of coming full circle in that, now, I think for one thing, people are now finding that literally these models can now overfit on the entire internet, the biggest models. But even, for applications other than kind of language modeling and image modeling and things like that, for scientific data, for engineering data, for health data, for lots of real world applications, the data is limited and is likely to remain limited. It's not so easy to gather. So I think that concern over data efficiency, really, it was always there. It's just that maybe over the last few years, people have kind of forgotten about it in a specific context of having so much data they don't need to worry about it.
Yeah, and I think the Bayesian framework really sort of puts this all together, right?
Yes.
So you really think about every bit of information. What is the value of it, and what does it bring to what new information does it bring?
Yes, and I think that was very much on my mind when I kind of started conceptualizing this, was basically how to marry the advantages of Bayesian inference and the efficiency, the data efficiency that brings, with the kind of the power of generative models. And you can see it in BFNs. There's really two parts, right? There's the Bayesian part, which is mathematically elegant and clean and gives you really like an optimal way of updating, beliefs given information so far. But it's also very limited. Like it only works on kind of individual variables in isolation. It can't do, a joint model over an entire image.
Yeah.
We don't have a closed form Bayesian update for something that complex. And that's where the neural network comes in, right? It does the contextual modeling where it takes all of these distributions and, models the interactions between them. But yeah, it seemed like a nice way of kind of, I think I definitely felt from the start that there must be a way of kind of exploiting this Bayesian efficiency and combining it with neural networks. And I mean, I should say, Bayesian neural networks have existed for a long time, but they were usually Bayesian about the parameters of the network. The idea was, okay, we'll start off with a distribution over the weights and update that, which is also an interesting research direction. And it's something that can definitely help to regularize models and, kind of constrain their complexity. But I would say it's not an area that people seem to be exploring that actively at the moment.
No.
We've talked a lot about kind of how BFNs came to be, right, and where the idea came from and how it relates to other frameworks. But looking a little bit towards the future here, Alex, where do you see BFNs going, right? What do you think the future is for them, and how do you think you'd ideally want to use them?
Yeah, so I think, that's a very interesting question. Of course, that's very much on my mind. I think one thing I want to get back to in the near future is this idea that, as I said, kind of, was it the seed of the whole thing, which is starting to look at the order in which the data is modeled. So at the moment, BFNs are still, they're, let's say, softer in the sense that they gather information gradually about the data, but they're still kind of predefined in the sense that they learn equally about everything in the data at once. And I'm very interested in the idea of a more dynamic system that behaves more like a human gathering information about a scene. And this is something that people have looked at in the past in the forms of like artificial curiosity and things like that. And it kind of goes into the field of active learning, sort of like choosing where to look in some sense. So that's an area, and it's interesting to kind of relate that back to the Alice and Bob scenario, because it kind of turns it from a one-way monologue with Alice just sending data to Bob and turns it into a conversation where Bob is asking questions and Alice is answering them. And so I think there's a whole kind of area to be explored there that hasn't really been looked at. So that's something I'm interested in near term. But maybe kind of looking beyond that, I think it's very interesting just to think about, well, how can we apply this? One of the key motivators was to be able to put lots of different types of heterogeneous data into a common framework, like being able to look at categorical data and continuous data and discretized data. And, there's even other variants, things like cyclical data, put it all into one kind of Bayesian flow framework. That should open the door to a lot of practical tasks that are kind of like somewhat difficult to tackle at the moment, or that at least require, cobbling together different tools. And so I think that's a whole other direction in terms of, which we're going to discuss more in the next episode, in terms of like, what are the practical applications, and of course, in particular, the applications to science and biology.
So all these different ideas about updating beliefs and using kind of a model that allows itself to learn what it cares about, right, and what's going to be important is really interesting mathematically speaking, but obviously really shines when we actually put it into some application. And we've been working towards this for the past year and a bit now, of actually getting these models and applying them to real world problems like biological data. And that's what we'll be discussing in the next episode. So we'll be discussing AppBFN2 and PropBFN, where we've actually taken this model, put some real world data into it, and see what happens and what we can actually do with that model.
Yes, and so with that, Alex, thanks for joining us. It was a really interesting discussion.
Thank you very much.
And to our listeners, make sure to join for part 2 in the next episode.